Okay, this is the last video for Chapter 2. This will correspond to the last two sections of the textbook, I think 2.7 and 2.8, if I'm remembering the section numbers correctly. But it's the sections on relations between statements and then finally testing argument validity using truth table method. Okay, so just as it's often useful to know whether an individual statement is a tautology, a contradiction, or a contingency. This is what we did in the last section. It's also often helpful to know what relations can hold between two statements. And there's three relations in particular that we'll be interested in. The first one is equivalence. And here's a definition of that. Two statements are equivalent if they have identical truth columns. So to test for equivalence, what you do is you construct what we will call a joint truth table, and which is just a truth table that has both of those statements on it, the two statements you're trying to assess. And you just compare their truth columns, right? The columns of T's and F's underneath those two statements. And if those columns are identical, meaning it's exactly the same pattern of T's and F's all the way down, then those statements are equivalent. If they're not identical, if there's even one row where they're different, then they're not equivalent. Okay, the next relationship, before we do any truth tables and work through some examples, we'll get all three relations that we're interested in. The second relation is consistency. And here's the definition. Two statements are consistent if, and only if, it's possible for them to both be true at the same time. And what that means basically is there a row where both of those statements are true. So to test for that, you do a joint truth table. And if there is any row, it only takes one, where they're both true, then they're consistent. If there's no row where they're both true, then those two statements are inconsistent. This is the only one that's a little bit tricky. And it's a little bit tricky because with the order of implication, with the relation of implication, there's an order issue. For the definitions and for the tests for equivalence and consistency, there were just two statements, and it didn't matter, which there wasn't a first and a second or an A and a B. You were just looking at two statements and assessing if the columns are identical or if they're both true at the same time. With implication, there is kind of an order. Right, you have two statements, but for the purpose of the definition, let's call one of those statements phi and the other statement psi. And these are, again, statement variables. They could be any statement. The definition of implication, in this case, implication will be, does phi imply psi? So there's an order to it. We could also ask, does psi imply phi? That would be another relation that could hold between them. But here's the definition for whether phi implies psi. If phi is true, then psi must be true. And here's how you test for that. This is going to sound complicated, this test, kind of writing this out, but when you see a few examples, you'll see that it's actually pretty straightforward to do. To see whether phi implies psi, you do a joint truth table for both of the statements, just like with implication, just like for equivalence and consistency. And you look for a row where phi is true and psi is false for that particular pattern. Okay, and we're going to call that a counterexample row. So if the question is, does phi imply psi? You're looking for a row where phi is true but psi is false. Okay, counterexample row. If there is a counterexample row, then phi does not imply psi. If there is not a counterexample row, then phi does imply psi. So it's pretty easy. You just look for a certain pattern. If it's there, then the answer to the implication question is no. If that pattern isn't there, then the answer to the implication question is yes. Okay. That looks complicated, but it'll be easy when you see some examples. Okay, here's two statements. Not P and Q, and not P and not Q. So step one is to do a joint truth table. And that's going to be one truth table that has all of the statements that you're assessing on it. In this case, we're assessing 2 statements. And you can see that I have statement 1 right here. This is column 6. And statement 2 is here in column 7. Okay, so I've got my joint truth table. Now, let's go through and ask the questions. First off, are 1 and 2 equivalent? Well, remember the definition of equivalence. You do a joint truth table, and if the truth columns are identical, then they're equivalent. If there's any difference anywhere, then they're not equivalent. And if you look, you can see that there is a difference, okay, right here. So because they're not identical, the answer is no. Now you might notice, oh look, there's another difference here, which is true, but that doesn't matter. As soon as there's any one difference, you've answered the question. You know that the answer is no. Okay, so they're not equivalent. What about consistent? This is a different test. They don't have to be identical truth columns in order to be consistent. Instead, there just needs to be some row where both of those statements are true at the same time. And if you look down their truth columns, you can see that in fact there is. So there is a row where they're both true, so they are consistent. Okay, so that's pretty easy, hopefully. You can see that it's trivial to assess those. As long as your joint truth table is correct, you just kind of look at the 2 truth columns and you make an easy assessment. Implication is also fairly easy. It's just a little bit more complicated. Okay, suppose the question is, does 1 imply 2? Okay, now that's going to be a different question than does 2 imply 1, and we'll assess that one in a minute. But right now we're asking, does 1 imply 2? So what we're going to look for is a counterexample row. And that's going to be a row where 1 is true, but 2 is false. So remember, here's 1, and here's 2. So is there a counterexample row? That's the first thing you want to find out. Yes, there is, right here. There's another one, but it only takes 1. As soon as you find a counterexample row, you can stop looking because you know the answer to the question. If there is a counterexample row, then the implication does not hold. 1 does not imply 2. Does 2 imply 1? Same thing, we're going to look for a counterexample row, but the counterexample row is going to be different. Now the counterexample row we're going to look for is a counterexample row where 2 is true, but 1 is false. Is there any row where 2, which is here, is true, but 1, which is here, is false? And you can see there isn't any such row. So there's no counterexample row, so 2 does imply 1. The answer is yes. By the way, I want to, before we move on to the next example, which is going to be pretty much the same as what we just did, we'll have 2 statements and we'll assess the 3 relations. Notice something. Look at the 2 statements. I sort of did this example on purpose. This is not P and Q, and this is not P and not Q. And in chapter 1, especially, this came up when we were translating statements, but also in this chapter a little bit. I mentioned to people that you shouldn't distribute tildes, that not P and Q isn't the same thing as not P and not Q. Okay? And that's why, sort of illustrating why these 2 aren't the same, is why I picked these 2 examples. If you look, these are not equivalent. Okay? Not P and Q, we could say doesn't mean the same thing as not P and not Q. And in particular now we can see what the difference means. If I say it's false that P and Q, then in both of these situations, where P is true and Q is false, P is false and Q is true, in both of those scenarios I've said something true. Right? Whereas if I had said not P and not Q, in those 2 scenarios, what I'd said would be false. So if you think through what these would mean, this would be something like, suppose I'm at home and someone asks, do we have milk and cereal? They want to have breakfast, so they want to know are there both of these things? I say, well, it's false that we have milk and cereal. Okay. Now, what I've said is true if there is milk but not cereal, and if there's cereal but not milk. What I'm just saying is that we don't have them both. Okay, if you need both of them, you're out of luck because we do not have both of those things. Okay. The only situation where I'd be lying is if it turns out we do have both of them. Not P and not Q is saying, really, we don't have either of them, right? It's false that we have milk and it's false that we have cereal, right? So if I say that, but it turns out we do have milk but not cereal, then I've lied, right? The only situation where this is true is when we lack both of them. Okay, so that's a sense in which they're both different. They differ in these situations. They're not equivalent. Okay, so that's why I selected this example, just so hopefully people can now see why these are different, even though if you just look at the symbols, it might look like you could distribute those. Okay, let's move on to the next example. Here's two statements, if A, then B. And statement 2 is, if not B, then not A. Now I want to point something out in this joint truth table. And this is, I don't know if it's super important, but it's something that comes up and students ask about. When you're constructing a truth table, with the atomic statements, you don't have any choice. Those have to go first, and they need to go in alphabetical order. Okay, so you don't have any choice in that matter. Once you've got the atomic statements, though, you might have some choice in the order in which you do the other columns. Usually I do negations of the atomic statements first, but I don't have to always. For instance, I could have done this statement, if A then B, that could have been column 3. Why? Well, because what are the components of A and B? Or I'm sorry, what are the components of if A then B? Just the atomic statements. I already have those by column 3. So because I already have columns for the components of this, I could do this on column 3 if I wanted. Okay. Could I do this on column 3? Well, no, because by the time I get to column 3 right here, I've only done A and B. I don't have the components that I would need for this conditional. I don't have a column for not B. I don't have a column yet for not A. So the real constraint when you're doing these truth tables and working from left to right is you can only do a column for a statement if you already have the components that you need for that statement, if there's already a column for those components. But that often will give you some freedom. I could have done not B and then not A. That would have been fine. I could have done this conditional on 3 and then not A, not B, and then this one. Okay, all of those would have been fine. The only thing I couldn't do is I could not do this one before a column for not B and not A had been done. So this one's going to have to show up after these two. Okay, so, and also what that means, sorry, I'm kind of spending some time on this, but it means that sometimes you'll have the freedom to make sure that if you're assessing two statements, you can put them at the end in order and just make it a little bit easier, right? I could have done not B, if not B, then not A here, and then if A, then B. They would have been out of order. And if I had done the conditional here, then I'd be comparing two columns that were far apart on the truth table. So I used the freedom that I have to try and put the statements I'm assessing together near the end. Okay, sorry for that diversion. Let's go back to our questions. Are 1 and 2 equivalent? Well, I'm comparing 1 and 2. Are they equivalent? Yeah, they are. True, false, true, true. True, false, true, true. Exactly the same pattern. There's no row where they're different. So they are equivalent. Next question, are they consistent? Different question. We're just going to look for any row where they're both true at the same time. Sure enough, row 1, right there, they're both true. Okay, before we move on, here's a conceptual question for you. We already saw that the statements are equivalent. They're the same pattern of T's and F's all the way down. Does that mean they have to be consistent? Okay, are any two equivalent statements going to be consistent? And you might think yes, but actually it's no. Okay, before I tell you how, think about it for a second. Pause the video if you want to think about it longer. I'll count to maybe 3 and then tell you why. Okay, here's why. If the two statements are contradictions. Okay, suppose if you did a truth table and the two statements that you're assessing are contradictions, that means they'll just be false all the way down, right? Just false, 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 false. Will they be equivalent? Yeah, they'll be equivalent because there's no difference. It's just false, 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 false. So they'll be equivalent, but they won't be consistent because there won't be any row where they're both true because neither of them is true on any row. Okay, so that's an example of how you could get equivalent statements that aren't consistent. Okay, so we know that they are equivalent and these two are equivalent and they are consistent. Now let's ask our implication questions. Does 1 imply 2? We're going to look for any row where 1 is true but 2 is false. And you can see here's 1, here's 2. There's no row where 1 is 2 and true is false. So 1 does imply 2. Now we can ask, does 2 imply 1? Same thing, we're going to look for a counterexample row, only now we're going to look for a row where 2 is true, but 1 is false. And you can also see there's no such row, so 2 does imply 1. Okay, now, another conceptual question. Our first question about these two statements was, are they equivalent? And we answered yes, they are equivalent. As soon as we know they're equivalent, can we tell immediately anything about the implication questions? And the answer is yes. Once we know they're equivalent, if we have two statements that are equivalent, then we know that 1 is going to imply 2 and 2 is going to imply 1. Why? How do you know that? Try to think that through. Again, pause this video if you want. I'll count to 3 again. Okay. Here's how you know. If the two statements are equivalent, what does that mean? That means that any row you look at, the truth value is going to be the same. When this is true, and vice versa. When this is false, this is false. Any row where 1 is false, they're both going to be false. If 1 is true, both of them are going to be true. Okay? Well, what does that mean in terms of whether you're going to find any counterexample rows? Well, remember, a counterexample row is a row where one statement's true, but the other one's false, right? So if we're asking, does 2 imply 1, we're going to look for a counterexample row where 2 is true, but 1 is false. That's going to be a row where the truth values are different, right? Counterexample rows, by definition, is a row where the truth values are different. Okay? Well, if the two statements are equivalent, we know there aren't any rows where the truth values are different, which means we know there aren't going to be any counterexample rows. And if there aren't any counterexample rows, then all of the implications hold. Okay? There's not going to be a counterexample to 1 implies 2, and there's not going to be a counterexample to 2 implies 1. So the answer is yes. If you know that two statements are equivalent, then you can tell, just on the basis of that information alone, whether 1 implies 2 or 2 implies 1. Okay, let's do another example. Now this is an example where I did use my freedom to make sure that the two statements I'm assessing are in order at the end, even though I might not have done them in exactly this order if I was doing something different, right? So notice I put not M here last. Normally I would do, if there was no other reason for me to go one way or another, I would just do the negations of the atomic statements right after the atomic statements. Normally I just go M, N, not M, not N. But notice Not M isn't a component in any of these other statements up here. So I don't have to do this before that because not M isn't a component here. And I don't have to do it before this, and I don't have to do it before that, which means that if I wanted to, I could hold off on not M until the very end. Okay. These two I could have done in either order. I could have done not N and then this conditional, whatever. But I had the freedom to manipulate things so that the two statements I'm assessing are 1, 2 in order at the end. You're not always going to be able to do that. Okay, but this time I could. Well, are they equivalent? No, look, row 3, different truth value, so they're not equivalent. Are they consistent? Sure. Row 4, they're both true, so they're both consistent. So 1 and 2 are consistent. Does 1 imply 2? We're going to look for counterexample row, a row where 1 is true but 2 is false. No, there's no counterexample, so 1 does imply 2. Does 2 imply 1? Well, there is a counterexample row. Look at row 3. 2 is true, 1 is false. So there is a counterexample row, so that implication doesn't hold. 2 does not imply 1. Okay, the next topic is going to be relations between 3 or more statements. We just did 2, and 3 is actually very similar to 2. These aren't new relations. These are the same relations, equivalence, consistency, implication, but now we're just going to be applying them. Instead of just applying them to 2 statements, we'll be applying them to 3, 4, however many statements. And equivalence and consistency are, it's trivial to sort of generalize these to 3 or more. A set of statements are equivalent if, this should be if and only if, they all have identical truth columns. Okay, so again, you just do a joint truth table that has all of those statements on it that you're assessing, however many it is. You compare all of their truth columns. And if they're all exactly the same, then that set of statements is equivalent. If there's any difference anywhere, then that is not an equivalent set of statements. Consistency, just what you'd expect. A set of statements is consistent, should be is, if there's at least one row on which they are all true. Okay, if there is a row like that, they're consistent. If there is no row like that, then they're not consistent or they're inconsistent. Okay, implication is the only one that's a little bit tricky. We're going to call it joint implication when we're dealing with more than 2 statements. And the reason is this. With implication, there's still a direction. Remember when we were dealing with 2 statements, we had to ask, does phi imply psi? And that was different from does psi imply phi? So there's still a directionality. But now the question is, well, we've got more than 2 statements. What are we going to do? Well, what the question is going to be is, we're going to ask, do phi 1 through phi n, and n could be any number. It could be 2, 3, 5, right? So there could be 5 statements here. Phi 1, phi 2, phi 3, phi 4, phi 5, whatever. But there's some set of statements. Do those statements jointly imply psi? And psi is just one statement. Okay, so the question is always going to be asked in that way. Does a certain set of statements, which could have one member, it could just be one statement, or it could be 5, however big it is, do they jointly imply this one single statement? And you assess it in pretty much the same way you do with when you're just dealing with 2 statements. You look for a counterexample row. If there is a counterexample row, the implication doesn't hold. If there is not a counterexample row, the implication does hold. So all that's exactly the same. The only change is that now when you look for the counterexample row, it's going to be a row where all of these statements, phi 1 through phi n, are true and psi is false. That's the counterexample row you're looking for. Okay, and this will be easy when we see some examples. So here's 3 statements, and you'll get this on the quiz. Here's 3 statements, and I'm just going to put numbers up here to just remind us this is statement 1, 2, and 3. Again, I was able to sort of get them in order on the truth table. Are 1 through 3 equivalent? Yeah, they are, which is kind of interesting, right? If you look at these 3 forms, they look like different statements on the face of it, but really they're all saying the same thing. If G then H is the same as either not G or H. Okay, and you might not see intuitively, but maybe it is, maybe it isn't. If you think it through, you should be able to see why that is the same. But anyway, are they equivalent? Yes, they are. You can answer that question just because you can see it's the same pattern of T's and F's all the way down. Are they consistent? Yeah. Look at row 1. They're all true. So it is possible for them to all be true. Now, the implication questions, the joint implication questions, are going to be framed like this. Do 1 and 2 jointly imply 3? Okay, so now I'm asking, do 1 and 2 jointly imply 3? So do these two, 1 and 2, jointly imply 3? So I'm going to look for a counterexample row, which will be any row where these 2 are true, but this one is false. And you can see there's no row like that. And again, we could have told that because we know that all 3 of these statements are equivalent. So we know there's never going to be a counterexample row even with 3 or more statements. But you can also just look down and tell that there's no counterexample row. So 1 and 2 do jointly imply 3. Also, if I asked do 2 and 3 imply 1, you would just look for a row where these are both true, 2 and 3, but 1 is false. And there's also no counterexample row there. So the implication does hold. And again, we would know that as soon as we know that they're equivalent. Okay, let's do these 3 statements. Here's the truth table. Remember, as always, you put your atomic statements in alphabetical order, even though that's not the order they were here. L sort of showed up first before K did, if you were just kind of reading these out. But always alphabetical order. And again, I managed to get them in order. L, this is 1, 2, and 3. So, are they equivalent? No. Row 1, there's already a difference right there. False, but that's true. So they're not equivalent. Are they consistent? Well, it's just going to need any row where they're all true. And you can see there's no row like that. So that set of statements is inconsistent. Let's ask some implication questions. Do 1 and 2 jointly imply 3? So we're going to look for a counterexample row. That'll be where 1 and 2 are true, but 3 is false. Right here, row 1. 1 and 2 are true, but 3 is false. There is a counterexample row, so the implication does not hold. No, 1 and 2 do not jointly imply 3. Different question. Do 1 and 3 jointly imply 2? Now I'm going to look for any row where 1 and 3 are true, but 2 is false. And you can see row 3 right here. 1 and 2 are true, but 3 is false. So again, there is a counterexample row, so that joint implication doesn't hold. 1 and 3 don't jointly imply 2. Finally, we could ask, do 2 and 3 jointly imply 1? And again, you can see no. Look here on row 4. 2 and 3 are true, but 1 is false. 2 and 3 are true, 1 is false. There is a counterexample row, so the implication does not hold, the joint implication. Let's do an example with 4 statements. Here I could not get them all at the end in order. There's no way to get B at the end. It's an atomic statement that has to go here. The rest I could get 1, 2, and 3 in order, so I went ahead and did that. But number 4 is here in column 2, but that's okay. It just means it's, I have to compare columns that aren't in order and are separated by other columns, but that's doable. Okay, are they equivalent? No, look, well, on rows 1 and 2, they're all true. So far so good. But then as soon as you get to row 3, there's a difference. These are false, 4, 1, and 2 are false, but 3 is true. So there's a difference. It only takes 1, so they're not equivalent. There's no need to keep looking once you spot a difference. Are they consistent? Sure, row 1, they're all true. 4, 1, 3, or 1, 2, 3 are all true. So they are consistent. Again, as soon as you spot any row where they're all true, you can stop looking. You know they're consistent. Maybe there's more rows where they're all true. Doesn't matter. I know they're consistent. Let's ask some implication questions. Joint implication. Do 1 through 3, so that's 1, 2, and 3, jointly imply 4? So we're going to look for a counterexample row where 1, 2, and 3 are all true, but 4 is false. I do not see a row like that. So if there's no counterexample row, the implication does hold, and there's no row where on that row 1, 2, and 3 are all true, but 4 is false. There's no row like that. Okay, do 1, 2, and 4 jointly imply 3? So now the counterexample row I'm looking for is 1, 2, and 4 are true, but 3 is false. And yes, there is right here. 1, 2, and 4 are true, but 3 is false. So there is a counterexample row, so that implication does not hold. Okay, and we could ask other questions too. Do 4, 2, and 3 imply 1, and so on. I'm not going to go through all those, but you could if you want to answer those questions. I want to get to the final topic of Chapter 2, which is argument validity. Remember, this is where we've been headed so far for the entire course. In Chapter 1, I try to convince you that at least in some cases, whether an argument is valid or not is a feature of its formal structure. So in Chapter 1, we spent time trying to take an argument in natural language, English, and put it in formal structure. And then in Chapter 2, the goal was to take an argument that was in formal structure and see whether it's valid or not. Now we can do that. Why? Because an argument will be deductively valid, here's a definition, or a way of assessing it, if and only if the premises jointly imply the conclusion. Now, I'll talk about that in a minute, because remember in Chapter 1, the definition sounded different. It really isn't different. It turns out they're equivalent, and that's what I'll talk about in a minute. But the definition in Chapter 1 was an argument is valid if it's not possible for all the premises to be true and the conclusion false. Okay? And now I'm saying, well, an argument's valid if the premises jointly imply the conclusion. Isn't that a different definition? No, it's not. And you'll see why in just a second, especially when we get an example up. So this is the pizza argument. Okay, so if I gave you the pizza argument, this pizza is either pepperoni or cheese. It's not cheese, therefore it's pepperoni. Right, this is a formalization of it. I should have a little line here, so 1 point off for me. If we do a joint truth table for the argument now, so now we're doing a joint truth table for the argument, the premises and the conclusion, all on one truth table. And we ask, do the premises jointly imply the conclusion? Well, where are the premises? Here's 1, here's 2, and here's 3. So they're at the end, but in reverse order. Okay? Well, do the premises jointly imply the conclusion? Is there any row where 1 and 2 are true, but 3 is false? No, there isn't. Okay? So the argument is valid, okay, because the premises jointly imply the conclusion. Now, what's the connection between that and the definition of validity in Chapter 1? Well, what was that definition? That definition was an argument's valid if it's not possible for all the premises to be true and the conclusion is false. Okay? If the premises are true, the conclusion has to be true. Okay? Well, if you think about it, that's exactly what you're assessing when you look for a counterexample row. Right? A counterexample row is a row where the the premises would all be true, but the conclusion is false. So if there's a counterexample row, that's the row that defeats the definition of validity. Right? That's a row where you have all true premises, but the conclusion is still false. Okay, so even though the definition sounds different, okay, once you unpack, let's go back here to this definition of validity. Argument is valid if the premises jointly imply the conclusion. When you understand what jointly imply means, it basically means if the premises are all true, the conclusion has to be true, or the conclusion can't be false, because that would be a counterexample row. So that's why this joint implication relation can be used as a test for validity. Okay, let's do some more examples. Here's an argument. I should have a line there after the L. Bad on me. And this might be a formalization of an argument like this. Trees are green, lead is heavy, therefore Elvis is dead. An argument where the premises just don't have anything to do with the conclusion, right? It just intuitively looks invalid. And we can see now with our test why it's invalid. If we do a truth table for this argument, it would look like this. Notice this is kind of a funky truth table. This is sort of degenerate case of a truth table because we don't have any compound statements. It's only atomic statements. But that's okay. It's still a legit truth table. We now just want to see if this argument's valid. Do the premises 1 and 2, and where's 1 and 2? There's 1, there's 2. Do 1 and 2 jointly imply the conclusion? The conclusion's here. So is there any row where 1 and 2 are true, but, I'm sorry, yeah, 1 and 2 are true, but 3 is false? Right here, row 5. So there is a counterexample row, so the argument's invalid. It's possible for the premises to be true, but the conclusion false. Let's do another example. And this might be a formalization of if ducks sink, then ducks are made of small rocks. Ducks do sink, therefore ducks are made of small rocks. This is an argument where everything is false. All of those premises are false. The conclusion is false. But if you look at it, you can still say, well, yeah, but intuitively, we sort of, in chapter 1, we're saying you should be able to just look at it and see that it's valid. But now you don't have to rest on intuition. We can do a truth table. Premise 1, premise 2, and the conclusion is here in the middle, actually. Is there a counterexample row? Do 1 and 2 jointly imply 3? Is there any row where 1 and 2 are true, but 3 is false? No, there isn't. So it's not possible for the premises to be true, but the conclusion false. The premises jointly imply the conclusion, so the argument's valid. One more example, and this will be the last example. Here's an argument. Now I've got the line, so I'm not losing any more points for not having the line there. We've got an argument with 3 premises and a conclusion J. I can't get them in order, obviously, but I can see. Premise 1 is here, 2 is there, 3 is here, and where's the conclusion? Here. Okay, so I'm asking, do the premises, which are here at the end, even though they're not in order, do these premises jointly imply the conclusion? Is there any row where these are all true, but that's false? Let's look right here. Row 4. I'm going to go ahead and make those so we can see. On row 4, premises are all true, conclusion is false. So it's possible for the premises to be true and the conclusion false, so that argument doesn't satisfy the definition of validity. So that argument is invalid. Okay, this video is over. This is the end of chapter 2. Study hard and good luck on quiz 2.